All right, guys, so hopefully I'm going to get, what do we got, about 20 minutes left. Let's get through all of the theory stuff, and that way you can all run away and get all of the questions done, okay? So, first things first, where's my pen? Oh no, Patrick, oh, who's not using their pen right now? Can I borrow it? Oh gosh. You're getting it back at a faster velocity than that. Yeah, right. Okay, so we looked at photons. Photons can interact with electrons, orbital electrons. They can capture them. It's all or nothing unless ionizing. And so we know it has to be the discrete energy corresponding to an allowed transition. But then you can also get electrons interacting with electrons. So, for example, we've seen our gas discharge tubes, for example, hydrogen, and we know that hydrogen pumps out, red and purple and orange and black photons and green highlighter, okay? Because what's happening is that our electrons are being accelerated across a potential. In our tubes, they are 4,000 volt accelerators, so our electrons, they go racing through, and as they do, they collide with the orbital electrons. Now, they might eject them, or they might fall back down, but when an electron is falling back down, you're looking at all the possible transitions it can make. And that's what we looked at when we sketched all of the lines going down to N1, all of the lines going down to N2, etc., etc. You can also burn your device or your substance. So, perfect segue here. We took our wire of sodium, and that's supposed to say NaCl. Okay. And when we placed it in the flame, we got that bright yellow flame. That's your emission spectra. Okay. Now, here is where the rules are different with electrons. Electrons can collide, so we've got to use the word incident electron and orbital electrons, just to make sure that we're naming them. They are different. The orbital electron's sitting there minding its own business, attached to the atom, and in comes an incident electron. They can impart an allowed amount of energy that corresponds, and then they will travel off with the remaining energy. Okay? So it still has to be an allowed quantum corresponding to possible transitions, but the electron can then say, right, you need 2.4, I've got 4, I'll give you that 2.4, and then it can recoil away with the remaining energy. It's just simple conservation of energy. Okay? So that is possible. Same deal. If the electron has more energy than the ionization, it can eject, and it will have the extra kinetic energy. So here's the problem. You need to be given one of the unknowns. If you have an energetic electron coming flying in and it ejects an electron, well, they would go flying off. Both of them would go flying away from the atom. But you need to know, well, the sum of the two, but you need to figure out one to be able to figure out the other. So in a question, you would normally be given one of the values. And it's just a simple balancing the books. It's conservation of energy. So let's just, I mentioned some numbers. Let's just do again two very simple energy level diagrams. Okay? So again, I've just given you two diagrams. I'm not telling you what levels they are. They might be the ground state. They might be N3 and 4. Who knows? But again, let's say in comes a incident electron. I'm going to use a different color because my photons were red. Here's my electron. And let's say that it has 3. I don't like your pen. 3.4 eV. Okay. That electron might say, thank you very much. I'm going to take that 3 eV from you, and then the incident electron will recoil with a residual 0.4. Okay? Now, there's no real equation. E final minus E initial equals E2 take E1, and we've just figured out that E final minus 3.4 equals 3. Is that right? No. It should be negative 3. No, it's not negative 3. Final minus initial. Is that going to work?
Yeah.
Negative.
No.
What have I done wrong here?
Shouldn't it be E initial minus E final is equal to 3? 5.4 or something.
Initial was 3.4. It lost its 3. There we go. It lost 3. Again, there's no real equation, but you have to just show your mathematical logic if you were asked for it. Let's go back now to this same negative 5 electron sitting there minding his own business. And in comes an electron that has more energy. Let's go a nice 7 EV incident electron. Strikes it. This guy, let's say that he travels off with EK equal to 1 EV. Okay? Okay, so you're...
How does that work then?
Well, he might... We don't know. We just say if he gets collided off, he then just, for some reason, he grabs 6 EV. 5 was required to remove it from the atom, and then it had a remaining 1 EV of kinetic energy.
I thought it was an all or nothing deal absorbing the energy.
No, that's photons.
A photon. Well, a photon could do this. Could be a 7 EV photon, but instead of it, the photon doesn't recoil and stretch out to be an infrared. The photon would be completely absorbed, and then this guy would go off with 2 EV. But it could recoil. It could just be stationary. There's an infinite possibility of combinations of energy, but it has to be conserved. So that's why I've said, if I didn't tell you what the kinetic energy is, you wouldn't know what the recoil energy of your incident electron is. So now you can go 7 equals... Yeah, all right, let's go energy initial equals energy final. Trying to think. 7 EV equals 5 plus 1 plus EK of your recoil, so therefore 1 EV. All right, so again, it's just balancing the books. Okay, let's now go here. Oh, we've got hydrogen again. Let's draw in our hydrogen. So negative 13.6, N equals 1. Let's do our 3.4, our 151, and our 0.85, and then our 0. So, okay, very crudely drawn. So, our incident electron is going to come in with 11 EV, and it's hitting a ground state electron. So that's important. We're saying we're starting there. Okay. The incident electron after collision and the wavelength of an emitted photon. Well, look what I've done. I've given only enough energy to get to this level here. Because if you look at the required energy to get to N3 is going to be nearly over 12 EV. So the only possible interaction here is going to be exciting that ground state up to N equals 2. Okay? So as we know, this electron will decay back down and emit a photon of light. Now we did that earlier this week, so we can figure that one out. But let's just figure out the recoil velocity of our incident electron. Okay. What have I done?
Are we going to be required to use like formula, or do you just come up?
All right. Well, let's just do the energy of the let's do the wavelength of the photon first. So E2 take E1 equals hc on lambda. So we've got our negative 3.4 minus negative 13.6. We got a 10.2. And again, we've got EV, so we've got to use Planck's constant in EV, 4.14. That should be a 10 to the power of 8. And we know 10.2, that's ultraviolet. That's going to pump out... Oh, I never solved it. That's a shame. That's a shame. Ratio, 4.14, 10 to the negative 15, bracket 3 times 10 power 8, bracket 10.2. Oh, count the numbers. 1, 2, 3, 4, 5, 6, 7, 100... 1210 nanometers. No, 121. 122. Okay. Then your E initial equals E final. So you had your 11 EV equals 10.2 plus your kinetic energy of your recoil electron. So our poor little electron travels off with 0.8 EV. Have I answered the question? No. We need velocity. So if you can recall, we need to convert... I'm going to blame this on Ed Elias. Look what you've done. You need to convert that. Okay. So we'll quickly do a little side mission, which I didn't do because I'm lazy, equals joules. And then we can go up and go V equals square root 2 EK on M equals, and you put the values in, all right? So I might get you to figure out the energy and then show all your working out. I got lazy. 5.30 times 10 to the 5 meters per second. Okay? Now I believe I've got one last question. Oh, we never really finished this, but I reckon you guys can do that. And I reckon you guys can do that. Well, in fact, no, I think we did. Did we do? No, we haven't done those B's and C's. Let's get over here, please. Because this one gets a little bit tricky. Because it turns out there's a few possible answers and it all requires just some little bit of arithmetic. So, consider hypothetical single electron. Well, we know the only single electron atom is hydrogen, so this is just a made up value, okay? You've got the energies. Let's just add in n equals 1, n equals 2, n equals 3, n equals infinity. 0 corresponds, sketch an energy which will produce lines as in an emission spectrum. Okay, so I'll just draw all of the lines down to n equals 1, all of the lines down to n equals 2, and all of the lines down to n equals 3. So that was A done. That was pretty easy. Indicate such a transition on the diagram with a bold line to ionize. So it has to start at the bottom and work its way up. So there's our bolded line. How much energy in joules? Ground state. Okay. So 0 minus 5. So 5 EV converted to that is 8.01 10. Oh, it's actually 8.0. I used too many sig fig last year. That's naughty. There's our answer. Okay, now calculate all of the lines in the absorption spectrum. And sketch the visible part. So down here, I've already sort of put some, oh no, I lost my, down here, we've got our schmear. Have I got my orange? Roy G, what am I missing? Bit of him. That'll do. That's your approximate regions, right? So we really only want, in this diagram, we really only want EV as high as 3.11 and as low as 1.77. So for this activity, we want to draw dotted lines on diagram A. We want to find the transitions that have energies corresponding to that. So let's just say, here's my dotted lines. Okay, let's just do some mental maths, but you'll put it down on paper. Can we go N1 to N2? 1 to 2, that would be around 1.9 EV. Yes, I reckon we're good there. Can we go... We can't go 1 to 3 because that's 4 EV. That won't appear on our visible absorption spectrum. Can we go 2 to 3? Yes, that would be 2.1. That's visible. Can we go 1? No, that's only that's going to be infrared. Could we go 3.1? Yes. Okay. So I'm kind of changing the question here. I'm going to write visible absorption spectrum. All right. If it just said absorption, you're basically going to do every single possible transition to 0, every to n infinity, every to n3, every to n2. You'll get 6. But the ones that we see are those. So here's what I want you to very quickly do is in each of these 3 sections, find the energies. So let's just do E2 take E1. Not energies, well, find the wavelengths. And then E3 take E2. And then E infinity take E2. All right. You might have seen I had the answers already written down, but those are the missing wavelengths that were captured by the electron, and so they would appear as the dark bands in your absorption spectra, okay? So that's a little fun activity for you to do now. And then that's pretty much me done with the talking. You've got photons interacting, you've got electrons colliding, and they've got their own separate rules that you need to be aware of. So can you guys complete these questions for the rest of the lesson? How long have we got? 5, 6, 7 minutes. Get working, please. And we'll stop the records.